Hello, Assalamualaikum. My name is Syahmi Shahabuddin bin Muhammad Sharin. I am group leader for the group 1 for BNT20903. Our project about shear force diagram toward beam railway bridge. Okay, this is our group member. We have my name is Syahmi, and then our group is Firdaus, and then Fahmi, and then Yaakob and Fatin Nabila.
Hello everyone. So right now it's about the problem statement. The main problem addressed in this project is that manual calculation of shear force diagram is very time consuming and prone to human error, especially when analyzing complex railway structure as a bridge, failures and platform grading. Another challenge in the railway structure are subjected to multiple loading condition. Engineers need to analyze the different axle loads, locomotive weight and load position according to railway design standard. As a result, the same calculation must be repeated many times. This repetitive process can lead to the calculation fatigue, which increase the risk of the mistake and many result in incorrect identification of critical shear force zone effective structure safety. In addition, manual calculation only provide static result. They do not offer the dynamic visualization of the shear force change along the beam, making more difficult for engineers to understand structural behavior. Although fine element analysis of FEA software can perform this analysis, it is often expressive, complex, and not suitable for quick preliminary design. Therefore, this project proposes a user-friendly Excel-based automation tool. We can automatically calculate the support reaction, generate a accurate shear force diagram, and provide a real-time visualization. This is improved engineering efficiency, reduce human error, and support better discussion making during the structure design process. Thank you. This slide explains the scope and limitation of the Excel-based shear force diagram or SPD analytical tools. First, let's look at the scope of the tool. The tool is designed to analyze simple support beam with a pin support of the left and a roller support of the right. This configuration ensures that a beam is statically determined can be solved using the basic equation of the static equilibrium. Next, the tool allows you to input three main parameters: the point load magnitude P, the main span length L, and the load position is A. This input can be changed easily, and the calculations are updated automatically. Based on this input, the tool automatically calculates the support reaction, namely RA and RB, without requiring any manual calculation. The beam is divided into the two analytical segments to determine the shear force before, after, and the applied point load. This enables the tool to accurately capture the sudden change in shear force at the load position. Finally, the calculated value automatically display as a shear force diagram using macro Excel. The graph update instantly when the input change, allowing engineer to visualize the shear force distribution in the real time. Now, moving on the limitation of the tool. First, the tool is limited to only one contracted point load per analysis. It cannot analyze multiple point load simulation. Second, it does not support more complex load conditions, such as uniformly distribution load, verifying distribution load, external moment, or moving train load that are common found in railway structure. Lastly, the tool does not generate a binding moment diagram or BMD. It focuses only on the shear force diagram, while the BMD analysis is assigned to another project group. In conclusion, this tool provides a simple, fast, and user-friendly solution for analyzing shear force under a single point load. Although it has several limitations, its efficiency improves the calculation speed, reduce human error, and provide a clear graphically visualization for preliminary structure design. Thank you. Okay, this slide presents the objectives of this project. The first one objective is development of a user-friendly Excel-based tool that can calculate the shear force diagram or SFD for a simple support beam subjected to single point load. The second objective is automate the calculation of support reaction and shear force value at the different section of the beam. This reduces a manual calculation save time, and minimize human error. The third objective is automatically generate an acute shear force diagram based on the used input. This provides the engineer with an instant visual representation of shear force distribution along the beam. Finally, the fourth objective is to provide a clear, well-organized, and easier to understand output. It can assist engineer and design in the making and more accurate structure design decision. In summary, this objective aim to deliver an efficient, accurate, and user-friendly Excel tool that simplify the shear force analysis while improving the productivity and reducing calculation error. Thank you.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Fahmi bin Muhammad Dia. Matrix number AN240058. So today I will talk about the design parameter. So there is a four design parameter that we include in this report, which is the first one is the beam span L and the point load P. So this beam span total length of the simply supported beam, which is in this report is span of 4 meters. So for the point load is the concentrated load applied to the beam, which is we use the load of 20 kilonewton. The second one is the support reaction RA and RB. So support reaction is a load position is in the distance from the left support to the point load. So from the left to the point load, which is in the middle. The load is placed at 2 meter from the left support. So from the left 2 meter from there. And the third one is the load position from left support. So this is the support reaction are calculated using equilibrium equation. So this is the equation in the below. We already include this. And the fourth one is the shear force and after shear force before and after point load. So the shear force in the beam is constant with each segment. So this is we already include this. For the given data, the shear force is 10 kilonewton before the load and negative 10 kilonewton after the load. So for the next slide is the design standard and code practice. So we include three of the code practice here, which is the first one is the Eurocode 2, design of concrete structures and concrete bridge. So the scope here is the design and detailing of reinforced and pre-stressed concrete bridge. So what is the application to shear force diagram? So this is applied to use to verify the shear capacity of concrete bridge members after the SFD has been determined. So the second code is which is we include is the Eurocode 3 EN 1993 slash 2, the design of steel structures, steel bridges. So the scope is the design rules for steel railway bridge. So the application in this shear force diagram is used to check web shear strength, stiffness, and overall structural safety using the calculated shear force. So the third one is the Eurocode 4 EN 1994 2. Design of composite steel and concrete bridge. So the scope that this include is the composite bridge design. So the application is used where the bridges consist of composite steel girders, and concrete decks to evaluate shear resistance and interaction. On to the next slide, the safety factors and material properties. So the exact value depend on the design Euro code, but commonly used value are there is already a list that already been by BEM, which is the parameter and the typical value. So for the factor of safety, unlimited limit state, the typical value is 1.35 until 1.50 for the dead loads. For the load factor, left train load, the typical value is 1.50 until 1.75. So the material safety factor still uh, gamma MO 1.0 until 1.1. So the material for the material safety factor, which is concrete, is 1.5, and the last one is the material safety factor, reinforcing steels. The typical value is 1.15. So, for railway bridges, additional dynamic effect from moving trains include through dynamic amplification factors, impact factors. The typical value is 1.10 until 1.30. And fatigue checks due to repeated train loading. So this is important. So they have to checks within the due for the train still going work. Okay, that's all from me. On to the next slide, the safety factors and material properties. So the exact value depend on the design Euro code, but commonly used value are there is already a list that already been by BEM, which is the perimeter and the typical value. So for the factor of safety, unlimited limit state, the typical value is 1.35 until 1.50 for the dead loads. For the load factor, left train load, the typical value is 1.50 until 1.75. So the material safety factor still uh, gamma MO 1.0 until 1.1. So the material for the material safety factor, which is concrete, is 1.5, and the last one is the material safety factor, reinforcing steels. The typical value is 1.15. So, for railway bridges, additional dynamic effect from moving trains include through dynamic amplification factors, impact factors. The typical value is 1.10 until 1.30. Uh, and fatigue checks due to repeated train loading. So this is important. So they have to checks within the due for the train still going work. Okay, that's all from me.
So now I am Muhammad Yaakob bin Jamil. Now I would like to explain about our design flowchart for this project. So in uh, this section explain the overall workflow used to generate the shear force diagram, which is we call as SFD, for a simply supported railway bridge beam subjected to a single point load. So let's start. We start from start, and next we input the parameters, which is L, A, and P. L refer to beam span, A refer to load position, and P refer to point load. Next, we move into the process. We calculate RA and RB, which is the reaction A and reaction B, by using the equilibrium equation. The equation is total Fy equal to 0, which is reaction A plus reaction B minus P equal 0. So next, the total moment A equal to 0, so which is reaction B times L minus P times A equal to 0. So we solve this equation is to solve the RA and RB, reaction A and reaction B. So next process, we calculate the shear force per segment. We determine shear force in each segment for the beam, each segment. So the next process, we generate plot data in 4 critical points. The first one is 0, and RA. Second one, A, which is the load position, and RA. Third one is load position A, RA minus P, the point load. And the last one is L, which is the beam span, and RA minus P, the point load. So next process, we plot the SFD graph. We by using the Excel and XY scatter, which is XY scatter chart, which straight line and markers. So the output we got from the Excel, the display result, uh, table of table of critical points for SFD graph. So that's how the workflow for our design flowchart. Next, I would like to explain about the shear force diagram SFD in generation process. So as we know, we spread it as at 4 points, which is at first point, in x coordinate we got 0 and y coordinate is RA. So at the first point is the starting point, which is shear force at this point. So the second point is the x coordinate we got A. This is the load point. So the y coordinate is still in RA. So the shear force immediately before this point load. So in the third point, the x coordinate is in point load and in the load position. So y coordinate is RA minus P. What is P? P is the point load of the beam bridge. So the shear force immediately after the position load. And the last point is, and the fourth point is, x coordinate is in L. L is the beam span. So y coordinate is RA minus P. So this is the ending of the load, ending of the point.
Okay, about spreadsheet development Excel tool. For this part, I will explain development from the Excel-based tool for the shear force diagram. The spreadsheet was designed to calculate the support reaction automatically and generate the shear force diagram for a simply supported beam with 1 point load. The Excel worksheet is arranged clearly into several sections, including the input data, support reaction, shear force table, plot data, final summary, and SFD graph. The purpose is of this layout to make the tools simple and user friendly. The yellow cells are used for the user input, while the formula cell calculate the result automatically. The final output graph is generated using an XY scatter chart. This slide show the input section of the Excel tools. The user only needs to enter three main value, which is the beam length, the load position, and the point load magnitude. For this case study, the beam length is 4 meters, the load position is 2 meters from the left support, and the point load is 20 kilonewton. These input value are then used by the spreadsheet to calculate the support reaction and shear force value. The load position must be within the beam span. Therefore, the condition is 0 less than less than L. In this case, the value of a is 2 meter and the beam span is 4 meters. So the input is valid. Okay, this slide explain the calculation section for the support reaction. After the input data is entered, the Excel tools automatically calculate the reaction at support A and support B. The formula for reaction at A is P multiplied by L minus A divided by L. The formula by reaction at B is P multiplied by A divided by L. Based on the case study, the beam length is 4 meters. The load position is 2 meter. And the position uh, load is 20 kilonewton. Therefore, reaction at A is 10 kilonewton and reaction at B is also 10 kilonewton. The equilibrium check show that RA plus RB equal 20 kilonewton, which is the same as the applied point load. This confirm that the calculation is correct. The last but not least, show the final output of the Excel tool. The beam is divided into the two shear force segment. For the segment 1, from 0 to 2 meters, the shear force is equal to RA, which is positive 10 kilonewtons. For segment 2, from 2 to 4 meters, the shear force is equal to RA minus P, which give negative 10 kilonewtons. The plot data consists of four important points: 0, 10, 2, 10, 2 negative, 2, negative 10, and 4, negative 10. The points are used to generate the shear force diagram. The graph is plotted using the NXY scatter chart, which straight line and marker. The graph shows a horizontal line at positive 10 kilonewtons, a vertical drop at x equal 2 meters, and another horizontal line at negative 10 kilonewtons. This vertical drop represents the location of the point load. The final scope of DSL tools is limited to the shear force diagram only. The bending moment diagram is not included in this part. Okay, thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Fatin Abdullah bin Rahman. My metric number is AN240127. To conclude this project successfully, we developed an Excel-based shear force diagram or SFD tool for analyzing a simple supported railway bridge with a single point load. The tool automatically calculates the support reaction and shear force values and generates the shear force diagram based on the user input. The result matches the manual calculation, proving that the tool is accurate, reliable, and easy to use. Overall, it provides a simple and efficient solution for basic railway bridge shear force analysis. For future improvement, the tool can be expanded to analyze multiple point loads, uniformly distributed loads, and moving train loads to better represent real railway conditions. It can also be integrated with the bending moment diagram to provide a complete structural analysis. In addition, improving the user interface with input validation, clearer instruction, and better graph formatting would make the tool more user-friendly. Finally, the tool could be developed into a more advanced application using MATLAB or Python to support more complex engineering analysis. That's all from us. Thank you.